Hi, and welcome to video 1.5, where we're going to talk about transforming data and then calculating something called z-scores. So let's take a look at our vocab. We actually started this in class. We started talking about shifting and rescaling. And so all of this video notes is under the assumption that you were in class and got to experience that little exploration that we did. This is just kind of wrapping it all up. On the backside, we'll be talking about standardized values and z-scores. As I mentioned, there's no calculator maneuvers here, at least nothing fancy or funky, but you do need a calculator because the calculating of z-scores does require some arithmetic. So we're going to make sure that we at least have a calculator next to us to sort of follow along. So let's move on to talking first about shifting and finalizing sort of what we noticed in class. So shifting, remember, that's when you're adding or subtracting a constant to every single data value. So when you do that, when you add or subtract by a constant to all the values, any measure of position, so remember position are things like median, mean, maximum, first quartile, it's just like this is the position. What happens is all position points are increased if we're adding or decreased if we're subtracting by that same constant. So here's an example. We've got this original sort of lighter distribution right here. And what we've done here is we have added 2, shifted it over 2 units to the right. And so we could see that the center right here, which was 1, has now been moved over here to 3. So it is now centered at the same, 2 to the right because of that. And all of the data points all moved over 2. Now, measures of spread, though, when we add a constant, are going to be unchanged. So standard deviation, IQR, range, those are unchanged when you shift everything over to the right or left by the same value. We can see over here in our distributions, they are identical in sort of, spread and in shape there. They're perfectly unchanged based off of just this adding of 2 over. So that's what we got going on there for shifting. So if you ever shift some data, that changes things like mean and median, but it will not mess with your standard deviation or your IQR at all. On the other hand, when we're dealing with rescaling, that's where we're multiplying or dividing all of the data by the same constant. In that case, when we rescale, then the measures of position are multiplied or divided, depending upon what you did, by that same constant. So things like mean, maximum, third quartile, things like that, they're going to end up getting moved based off of that scale factor there. So here I have an example. Here's the original distribution. And what we've done is we've multiplied everything by 2. So what did that do? Well, we can see that originally there's your center. And now our center is here at 2. So we have now multiplied it all by 2. Measures of spread, though, okay, this time around not unchanged. This time around also multiplied or divided by that constant. So measures of spread. You can see it visually over here because we could see that we had a skinnier distribution, and now it looks like it's about twice as wide over here once we've done that scaling. You can also see it in the numbers here because we have that the standard deviation was 0.25, and we landed on it now being 0.5. It has doubled there. The other interesting thing that's happened here is that what has happened is that the distribution also kind of got shorter. We could see that here we've got this big, tall original peak, and now it's down here. That actually should make some sense here, okay? Because something that's sort of interesting about all these is that the area under these curves here is always going to be identical. It's going to be 1, ultimately, is the idea there when we're thinking about area. But when you shift it and you do your rescaling, the area under the curves actually stays the same. That's pretty obvious up here in the shifting, right? It's like you can see, it's like, well, that particular distribution has just moved over. Obviously, that's the same area. But it's going to be true here because it's like, oh, wait, like all of my area was sort of in here, nice and tight and skinny. Now that I've widened it out, I have to maintain the same area, so I can't be as tall as I was. Once you go wider with it, that's going to bring the peak down a bit there. So that's something interesting to sort of point out, is that the area inside there has stayed exactly the same, even though you have rescaled it. Why don't we go ahead now and move along down to here. So suppose that a small business is trying to think about, giving a little boost to their employees' salaries. And so here's a table that has all their hourly wages in that table. And so first, why don't we go ahead and take a moment to go to our calculator, enter this data, and we're going to use the one variable stats in order to find all of this information here. We're not going to do it by hand. We're going to let the calculator do it. So enter it, find it, and when you're ready, press play again, and you'll see I have all the numbers here. So hopefully you got what I have here now, okay? If anything went wrong, double check that you typed in your data correctly, double check you're using the correct list, but this is what you should have come up with. So now let's think about how these things are going to change based off of some different ideas for giving them a little boost in their salary here. So suppose what they really want to do here is they go, hey, we're going to just bump everybody's pay rate up $5 per hour. So what would that do? Think about what kind of transformation that is. Is that a shift or is that a rescale? Think about the notes that you have there and try to come up with what are all the different new values from this based off of a $5 raise. And then hit play when you're ready to see all the answers again. So here's what you should have come up with. So all the numbers are there. You'll note that the only things that changed were anything that is a position point, not measures of spread. So IQR, identical still. Range, identical still. Standard deviation, identical still. But everything else has been added up by 5, moved to the right by 5. And that's consistent because this is a shift of +5. It is not a rescale, so we're not multiplying, thus the distribution will look identical, just moved over to the right by 5 units. No change in spread. Let's move along to the next one, though. What if they decided, hey, we're just going to increase your salary by multiplying it by 1.5? Now, what would your numbers be here? Think about it, and then work it out, and then press play when you're ready to see the answers. So by rescaling here by 1.5, we are going to go ahead and just multiply every particular value by 1.5. So this is our new sort of summary statistics here. So you'll notice this time around, we did see a change to standard deviation and range and IQR because it's a rescale, not just a shift over. So now moving on to the backside. So transforming data might seem like something that's like not super useful. Yeah, we can do playing these like what if, games with like, oh, what if we, raise everybody's salary by $5? But it like, is that really what we use it for? No. More often it gets used for like, converting units. So if you have data that's in centimeters and you want to switch it to inches, you can do that by rescaling or I guess in this case, or reshifting, like scaling in this particular case, but sometimes you can just shift. But the real thing is that we're going to be doing some rescaling and shifting constantly in this class in order to help us find something called the standardized values, okay? So to standardize your data, you do the following here. So you start with some data that's centered around X bar and has a standard deviation of S sub x, okay? The first thing you do to start your standardizing is you subtract all the data values by x bar. Well, what's that going to do? That's going to now center our data around 0. So if it was centered at x bar and then you subtract by x bar, you are now centered at 0. So you can sort of see down here in this example here, we have some distribution that seems to be centered around, I don't know, 12-ish. So we're going to go ahead and say minus 12 over here. My pen went wonky. So we're going to go ahead and subtract by 12. That's our x bar. And now you can see we are centered at 0 in this particular case. So it gets us centered around 0. Everything's centered around 0. 0 is a pretty nice number. Allows you to have some negatives and positive values in there. All right, but then we're not done. The next step in standardizing is to divide all the data values by S sub x, the standard deviation of our data set. What does that do? Well, it's going to scale all the data down to the number of standard deviations from the mean. So over here, originally we had, standard deviations of, it kind of looks like the standard deviation is about 3 there. But by now scaling it down, we now have standard deviations of 1. Everything is a standard deviation of 1. Now all of your data actually represents that. The way we sort of describe it would be like, oh, hey, like my standardized value is like a 4. That means that that data point is 4 standard deviations from the center. So that's what's been done here. We did a little dividing by 3, it looks like, and that got us this new distribution here. So let's practice this idea of standardizing values first. So let's take, for example, the small business that's thinking about and giving a raise to their employees. We knew that their mean hourly wage was $24 per hour with a standard deviation of about $1.71. And so what we want to know is, what is this standardized value, z-score here, for an employee who earns $28? And then how do you interpret that? Well, let's go ahead first and calculate it. So first we'll find the z-score. So we're going to take our data point, 28. We're going to subtract by the mean, which is 24. And then we are going to divide it all by the standard deviation. So if we subtract the top, we get 4. And we divide that by 1.71, and we get that our z is approximately 2.34-ish. It's okay to round. So what does this z value mean for us? It means that this employee has a hourly rate that is 2.34 standard deviations higher than the mean. So this standard, so it gives us an idea of like, oh, compared to everybody else, where is this particular employee's hourly rate? Turns out it is almost 2.5-ish standard deviations above the average there, which means they're getting sort of paid much higher than most of the other people at this company. So that's a z-score there, okay? So z-scores and standardized values are exactly the same. Z-scores have us always centered at a mean of 0 with a standard deviation of 1. And it doesn't change the shape of the distribution, so if it's roughly symmetric, it still will be when you do these changes. If it's roughly skewed, it will still be. If it's uniform, it still will be. So that's the beauty of all of this. And so there's that formula there. Z is equal to x minus x bar over s sub x. So what's the point of all of this? Like, we standardize the value. Good for you. You can interpret it. Great. I like it. What it's really nice for, though, is being able to actually compare distributions, values in different distributions more easily. So here's an example here. So let's say a student Cabello took a chemistry test, okay, and a Mandarin test the same week. Camillo got a 87 on the chemistry test and a 56 on the Mandarin test. So if you were just looking at those raw numbers, you would think, oh, so he did better on the chemistry test. But you don't know what the averages were, how spread out things were. So we come in over here now, and we're going to take a look, and we see, oh, wait, so the chemistry test, the average was a 79 with a standard deviation of 9. So it looks like Cabello did better there. Like, oh, okay, you got higher than the average. Good job. And over on Mandarin, the average was a 50 with a standard deviation of 5. So again, did better. Well, so now it becomes a little bit tougher. How do you know which one he did better on because he did better than the average on both? Well, that's where then the standard deviations come into play that help us figure this out. So take a moment, okay? I'm not going to do this one for you. I want you to calculate the z-score for both the tests and Cabello's particular data, and then make a decision. Which one did he do better on? How do you know that? So make sure that you try this out on your own here, and the last one there. So the last one gives us some slightly different information. It says here that Cabello has a classmate, Gertrude. Gertrude scored on the chemistry test 1.4 standard deviations below the average. So what was their score then is the question here. So it's working a little bit backwards. So I'll give you a little hint there. It's working backwards. You're not going to use the z-score formula the way we have been using it. You got to think about what information you do have, and what information's missing, and how to try to find that missing information by using your algebra skills. So I leave that to you as well. When we come into class, we'll talk about both of these here, the work that went into it, and how you interpreted things. I'll see you in class.